Hello, and welcome to the Mathematicians Podcast, the podcast where we follow the fascinating stories behind the figures that count in the history of mathematics. I'm Benjamin Cornish, and today I promised you a double bill of two smaller mathematicians. And I'm somewhat regretting this, however, as it turns out I can write enough content on each. That means this episode has become a little long, and so I shall keep my introductory story very short. Let's just say I used to have a friend who was a pirate, and he bought me my first ice cream van, then we did some maths, and we can begin. Dionysodorus of Amisus lived in the 2nd century BCE, hailing from the city of Amisus in the southern coast of the Black Sea, modern-day Turkey. At the time, Amisus was a thriving Greek port city, swept up in the intellectual afterglow of Hellenistic expansion. We don't have extensive records of Dionysodorus's life. Ancient biographies are patchy, especially for people who didn't win wars, rule kingdoms, or invent tragic theatre. Luckily for us, there are two mathematicians called Dionysodorus who lived around the same time, and based on historical accounts from Pliny the Elder or Heron of Alexandria, it's really difficult to know which is which or who invented what. So I will be taking the artistic license of assuming they were the same person. Dionysodorus applied geometry to physical problems, extending the field in directions that were quite literally down to earth. Now, let's talk about Dionysodorus's most mathematically striking achievement, his method for calculating the volume of a torus. And yes, we do believe he was the first person to name it as such. This is the donut-shaped solid generated by rotating a circle around an axis outside of the circle, a treat for the geometrically inclined. The source of this comes, intriguingly, from the work of Heron of Alexandria, writing some 2 centuries later. Heron tells us that Dionysodorus had found the volume of a torus, and not just any torus, but one created by rotating a circle of radius r about an axis in its plane at a distance of capital R from the centre of the circle, giving us the resulting formula of 2 pi squared r squared times by capital R. Is that not just a beautiful expression? It's ahead of its time. To derive it, Dionysodorus had to understand something akin to what we now call integral calculus, or at the very least, the method of indivisibles. This was centuries before Cavalieri, and nearly 2 millennia before Newton or Leibniz started arguing about notation and coffee consumption. The key idea is this. You take the circle being rotated, imagine it sliced into infinitesimally thin elements, and calculate the volume swept out by each element in rotation. This is kind of proto-integration. Talk about going around in circles with purpose. Now, was Dionysodorus actually using integration as we know it? Well, no. But his method, which likely relied on geometric decomposition, shows a deep understanding of how rotation can generate volume. This is the same spirit that Archimedes had for his technique in finding the volume of a sphere using the method of exhaustion, which we discussed back in episode 24. Interestingly, the torus volume formula appears in modern calculus courses as an example of using the shell method. It's a classic case of ancient geometry making a surprise cameo in your first year undergrad maths class, right between U substitution and please God let the exam be multiple choice. Dionysodorus didn't stop at toruses. He also tackled a problem involving slicing a sphere, specifically finding the volume of a cap of a sphere. You might think this is just another geometry problem, but it's actually a leap in conceptual understanding. It requires seeing a 3-dimensional object in terms of its cross-sections. Let's set up the scene. Take a sphere. Now slice it with a plane not through the centre. The result is a spherical cap. And the question is, what's the volume of that cap? Well, we know the answer. It's 1/3 pi h squared times by 3r take away h, where r is the radius of the sphere and h is the height of the cap. This formula is standard today, but Dionysodorus was among the first to consider problems like this. While we don't have a direct record of the derivation, his approach likely involved using known volumes, possibly cylinders or cones, to approximate or subtract from the sphere, much as Archimedes might have. The ability to conceptualize partial volumes of curved surfaces was a serious advance in spatial reasoning. Even today, when asked to visualize slicing a sphere, most people just capitulate. It's not just cutting edge, it's cutting sphere. So far, Dionysodorus has flown under the radar for most maths textbooks. But if there's one area where he really deserves top billing, or at least a dedicated footnote, it's in his confrontation with the cubic equations. That's right, he took on degree 3, the middle child of polynomial equations, the triangle of algebraic difficulty. To set the stage, let's rewind to a familiar problem in Greek mathematics, the doubling of the cube, also known as the Delian problem. Legend has it that the citizens of Delos were told by the oracle that to end the plague they must double the volume of their altar, which was in the shape of a cube. Easy enough, right? Except doubling the volume of the cube requires you to construct a new cube whose side is the cube root of 2 times the original. And the Greeks, limited to straight edge and compasses, found that you can't do that. Doubling a cube precisely is impossible under those restrictions, which is just another way the universe says you can't always get what Euclid wants. Now enter Dionysodorus. He used a geometric construction involving conic sections, specifically a hyperbola and parabola, to solve the cubic equation, underlying the doubling problem. Let's unpack that. The general formula of the doubling the cube problem boils down to solving x cubed equals 2a cubed. We're given the side length of the original cube. We want to find x so that the cube with the side x has twice the volume, and that means x is equal to a times the cube root of 2. So the challenge is construct a length proportional to the cube root of 2, and this is not compass and straight edge friendly. But Dionysodorus' approach, this using the conic intersections, it's a method that gets around the restrictions by introducing curved lines into the mix. We don't have his original writings because apparently ancient geometry wasn't written in acid-free paper, but later authors, especially Euclid of Ascalon, quote his construction method. And what Dionysodorus does is this. He sets up the two curves, a parabola and a hyperbola, whose intersection encodes the solution to the cubic. In geometry meets algebra meets, I bet I can draw something that solves this for me. So the solution was not a number, but a construction. A drawing with measurable dimension. Dionysodorus gave a method that would let you build this length using curves. It's a graphical root finding technique, long before Descartes or Newton or your TI-84. Now, this does sound like a familiar technique because we have solved the Delian problem in the past of doubling the cube, but this method doesn't just solve one cubic. By changing the positions and the parameters of the curves, you could generalize it to solve a class of cubic equations. In that sense, Dionysodorus built an analog algorithm. Eat your heart out, slide rules. Now let's fast forward a millennium or two. The equation x cubed equals 2a cubed is algebraically simple, but historically slippery. It's unsolvable by ruler and compass, but geometrically solvable by intersecting these curves. And this insight that geometric constructions can solve algebraic problems is one of the stepping stones to modern algebraic geometry. Today, we'd solve the equation x cubed take away 2a cubed equals 0 using the cubic formula. But that wasn't discovered until the 16th century, when Italian mathematicians like Del Ferro and Cardano finally cracked the general cubic, often under competitive secrecy that makes modern academic publishing look positively wholesome. But Dionysodorus did it over 1,000 years earlier, without symbols, without algebra, and without getting banned from ancient Twitter. His method influenced later mathematicians, particularly in the Islamic Golden Age. Mathematicians like Al-Khayyam extended conic intersection techniques and gave more systematic treatment of cubic equations, often citing Greek works, including Dionysodorus, as inspiration. So where does Dionysodorus sit in the mathematical pantheon? He's not as well remembered as Archimedes, Euclid, or even his solid loving cousin Apollonius. But that's not a reflection of his importance, just the quirks of history, and which scrolls happen to survive being used as late-night kindling in some Roman villa. What sets Dionysodorus apart is his seamless movement between abstraction and application. He didn't just describe the world, he helped build it, sometimes literally. His work on volumes shows a level of mathematical sophistication that wouldn't be matched for centuries, and his interest in practical problems kept geometry grounded. If Apollonius was the poet of curves and Archimedes the tactician of solids, then Dionysodorus was the engineer of space. Less flashy, but utterly essential to the machinery of ancient thought. That's one way to make the cut. Our second subject is Hypsicles of Alexandria, a Greek mathematician and astronomer active sometime in the 2nd century BCE, maybe around 150, give or take a solar eclipse. As usual, the dates are a bit fuzzy, but ancient biographers weren't big on calendars, and history has a way of losing the receipts. But we do know a few things. Hypsicles was from Alexandria, which, as you'll remember from about half of the episodes in this series, was the place to be for anyone interested in books, scrolls, or geometric obsession. The Library of Alexandria, still tragically better known for how it burned down than how it burned through knowledge, was a hub of scholarship, and Hypsicles was working right in its glow. He is best known for two things. First, for extending Euclid's elements by adding what we now call Book 14, and second, for writing a small but potent work called On Ascensions. It's got astronomy, geometry, fractions, and a healthy respect for the zodiac. It's also got a sense of mathematical drama, which, if you've ever seen someone try to explain precession at a dinner party, you'll know is quite a feat. Hypsicles knew how to stitch together maths and astronomy with subtlety, elegance, and just enough philosophical spice to keep things interesting. Let's start with Book 14 of the Elements, a curious mathematical appendix that Hypsicles is often credited with compiling, expanding, or possibly even writing entirely. There's debate among historians because, of course there is, but most agree Hypsicles had something to do with it. Now, you may remember that Euclid's Elements is a 13-book masterpiece of geometric structure, starting from basic definitions and building up to complex propositions. It's like the Lego technique of logic. Click one brick in the wrong place and the whole crane collapses. Book 13, the original final act, focuses on the Platonic solids, especially the regular polyhedra inscribed in a sphere. It ends with an elegant result, that the construction of the 5 Platonic solids and the ratios of their edges. But Hypsicles said, wait a minute, let's take this one solid further. Book 14 continues the discussion of incommensurable lines, that is, quantities that don't share a common measure, like the side and the diagonal of a square. It focuses in particular on the dodecahedron and icosahedron, and compares their inscribed spheres, the so-called in radius, and the relationship between their side lengths. One of the main results in Book 14 is the proof that the ratio of the surfaces of the dodecahedron and icosahedron inscribed in the same sphere is the same as the ratio of the squares of their edges. That is, surface area of dodecahedron divided by surface area of icosahedron is equal to edge length of dodecahedron squared divided by edge length of icosahedron squared. That's not just nice to look at, it reflects a deep symmetry in the geometry of regular solids. It's mathematical feng shui. This comparison required detailed knowledge of the internal angles and face structures of these solids, pentagons for the dodecahedron, triangles for the icosahedron, and their projections onto a sphere. It's a perfect blend of algebraic proportionality and geometric spatial reasoning, and it builds naturally on Euclid's work, showing how the legacy of Platonic geometry continued even after the official end of the Elements. Hypsicles was, in a sense, doing what any good mathematician does after reading Euclid, writing fan fiction. Let's move on to On Ascensions, or Anaphorikos, a compact astronomical work with a mathematical soul. Hypsicles here makes a foray into the cosmos, not with myths, but with maths. The title refers to the ascensions of the zodiac signs, the amount of time each sign takes to rise above the horizon as the Earth rotates. This time varies depending on where you are on Earth and what time of year it is. In other words, ancient Greeks understood time zones before it was cool. Hypsicles was interested in equal divisions of the celestial circle, the ecliptic, and how these segments translated into time. Imagine dividing the circle into 360 degrees and then asking how long does it take from a given point on Earth for each 30-degree zodiac segment to rise. Spoiler, The answer is not always 2 hours. The Earth's rotation and the obliquity of the ecliptic, the tilt of the Earth's axis, mess with that. The ascension times vary depending on your latitude, and Hypsicles noted this and gave tables for calculating the risings under certain assumptions, particularly at the latitude of Alexandria. Here's where the maths gets spicy. To make the calculations manageable, Hypsicles divided the zodiac using a base 60 system inherited from Babylonian astronomy. This is the sexagesimal system. It's why we still have 60 seconds in a minute and 360 degrees in a circle. You can blame the Babylonians the next time you forget how to convert back to radians. Hypsicles gave specific times for the risings of each zodiacal sign and introduced fractional notation that blended geometry and astronomy. He wasn't just throwing numbers at the stars, he was tracking their motions with precise numerical tools. And this wasn't idle curiosity. Knowing when certain stars or constellations rose was critical for navigation, agriculture, and religious rituals. If you want to know when to plant your crops or sacrifice your goat, you'd better know when Virgo is making her entrance. So On Ascensions, we see Hypsicles working at the seam of astronomy and geometry, not predicting eclipses, but building a model of the heavens that used angles, fractions, and spatial reasoning. It's like trigonometry's awkward teenage years. It's not fully developed, but it's definitely experimenting. Let's linger on Hypsicles' use of approximations and measurement, because this is where we see the transition from classical Greek geometry to the more flexible numerical reasoning that would come to define later mathematical cultures. Greek mathematics famously preferred exactness, lines, shapes, proofs, all tidy, rigorous, and constructed with compass and straightedge. But Hypsicles shows a willingness to bend the rules, especially in astronomy, where exact values weren't always feasible. For instance, on Ascensions, he deals with the division of time into fractions and doesn't shy away from irrational numbers or compound ratios. This is similar to what we saw with Archimedes, who approximated pi as between 3 1/7 and 3 10/71. Hypsicles uses approximations, not as a failing, but as a tool. He acknowledges the complexity of celestial mechanics and models them as best he can using the tools of Greek geometry, Babylonian number systems, and a healthy respect for just rounding it already. His hybrid approach represents a shift in Hellenistic thinking, away from pure geometry and towards something more pragmatic. It's not quite algebra, but it's leaning in that direction, like a mathematician trying to peek over the fence at the future. In mathematics, we often ask the question, is it true and is it useful? And on a good day, it can be both. This foreshadows the later work of Ptolemy, who would famously combine geometry, trigonometry, and empirical observations in the Almagest. In fact, some scholars think that Hypsicles' work influenced or was used by early drafts of Ptolemy's models. One of Hypsicles' most lasting impacts is not a theorem, but a decision. He's often credited as one of the earliest editors to arrange Euclid's elements into the standard 13-book form, possibly even adding books 14 and 15 to complete the volume. This act, part editorial, part mathematical, was an attempt to preserve, organize, and transmit knowledge. He wasn't just a mathematician, he was a curator of concepts, a librarian with a compass, a geometry geek with a strong opinion about pagination. And this is no small feat. Mathematical texts of the ancient world didn't come with tables of contents, chapter headings, or user-friendly diagrams. Preserving them involved copying, interpreting, and occasionally guessing what on earth the author meant by "let ABC be a circle" again. Hypsicles helped ensure that later mathematicians, Islamic scholars, Renaissance thinkers, Newton himself, would inherit a clear, accessible version of Euclid's masterwork. He helped give the elements its final form, and in doing so, gave Western mathematics its syllabus. Let's talk modern maths. Where does Hypsicles still matter? Start with spherical geometry, the kind of problems Hypsicles tackled in On Ascensions, converting circular arc lengths into times, modelling motion on a sphere, dealing with projections. They're still relevant in astronomy and geophysics. Satellites today use far more complex models, but the basic concept mapping the sky onto time is timeless. His geometric comparisons in Book 14 are also conceptually close to modern solid geometry and trigonometry. Relationships between surface areas and edge lengths are now taught in middle and high school, though rarely with quite so much polyhedral flair. His hybrid number work, Babylonian Fractions within Greek Proofs, foreshadows the entire idea of scientific computing, blending discrete and continuous maths to get results that aren't exact but are useful. In this way, Hypsicles is something of an unsung bridge, linking rigorous geometry with the messy world of physical measurements and motion. He measured the heavens, but he kept his feet on the spreadsheet. And in case you're wondering, yes, there is a lunar crater named after him. Hypsicles sits on the moon's eastern edge, gazing forever at the Earth, as if to say, don't forget to adjust for latitude. And that's it for today's episode of the Mathematicians Podcast. If you have enjoyed listening to me today, then thank you. Please do leave a comment or share the episode with 50,000 of your friends. If you can't wait until next week, then you can follow me on Blue Sky at mathematicians-pod to hear about all my other projects. I do the occasional YouTube video, and I've started a math chat show. Come check it out. It's quite fun. Next week is a big one, with a mathematician taking the stage solo. It's Hypsicles of Nicaea. I'm sure you will be over the moon to hear about his work, and I'm sure we will all agree that a new star has been born. Next week with Hypsicles. Until then, goodbye!
The music today is Dance Macabre Finale by Kevin MacLeod. You can find more information in the show notes.